Hello, we are the Data Center Group. I'm Haley Hershey,
I'm Ariana Marcelo.
And I'm Webster Lawrence.
and we're excited to share results with you today. Now for a quick overview of our project, we have three main phases. The first is modeling a hypothetical data center in the OpenStudio. This is basically taking the basic build of the building and putting in the HVAC system, the electrical system, the loads, and all of that into OpenStudio. The second is optimizing the building as much as possible, which in this case is defined as reducing energy consumption, CO2 emissions, and cost, while still fulfilling all the building's needs. The third is to create a business case analysis between the base model that we have created and the final model that is the most optimized.
So this project has plenty of real-world application. For example, our friends from HDR, Lewis and Griffin Green, basically use OpenStudio to make real engineering design decisions. So this project gave us an opportunity to learn a lot more about OpenStudio, about energy modeling in general. And our data centers are becoming a lot more important in today's day and age with the Internet of Things. As you can see, like Amazon, for instance, is moving to Arlington, and they're going to be building plenty of more data center buildings.
As mentioned, we used OpenStudio. It's software where we were able to create an energy model of an office building with a data center. We were also able to run simulations in order to find the total energy usage for each of the parameters that we have set. The great thing about OpenStudio and modeling in general is you can input a plethora of variables, some of which we have listed here, such as weather file and design days, schedules, constructions, and materials, etc. Not only do you see how these variables affect the overall design, but how they affect each other. This will not be possible with traditional methods because it would take far too much time and money.
To show you just how involved OpenStudio is, we wanted to show you an example. All the way on the left, you see a typical HVAC loop where you have the demand side, which is rooms that need to be heated or cooled, and the supply side, which is the equipment that heats or cools them. In the red circle is a cooling coil, which cools the air that goes to the rooms to cool them. In the next box over, that is another loop between the cooling coil and the chiller. The cooling coil becomes colder by the chiller cooling it. The next slide over is is the loop between the chiller and the cooling tower. After the chiller is done, after the chiller takes the excess energy from the cooling coil, it gives it to the cooling tower to dissipate into the air, thus starting the cycle over again.
For the business case analysis, we will be implementing life cycle analysis on our models. Life cycle analysis basically assesses the potential environmental burdens and impacts associated with a product or system in its life cycle. There are normally several stages associated with LCA, such as raw material extraction, manufacturing and assembly, transportation, usage, and disposal. However, for this project, we're only focusing on usage because the energy used that is recorded by the OpenStudio model is during the use phase.
So another tool that we used in class was the NREL database, and we used it also as part of this project, as part of the BCA analysis. The NREL database is energy and material flows into and out of the environment that are associated with producing a material, component, or assembly in the U.S. So basically, we use the NREL database rates to calculate the total CO2 emissions in pounds, as well as the standard utility rates that are used in the real world that were provided by Griffin and Lewis. These rates were for natural gas, around 50 cents per therm, and for electricity, around 1.5 cents per kilowatt hour. One of the main components of our model were the different chiller systems that we use. So what's a chiller? A chiller basically removes heat from a load and transfers it to the environment. The two main chillers that we would use in this model are air-cooled chiller and water-cooled chillers. Basically, water-cooled chillers use a water reservoir in a refrigeration cycle to remove heat. It utilizes cooling towers, which leads to higher efficiencies than air-cooled chillers. They're also generally smaller than air-cooled chillers and last longer than air-cooled chillers. One of the downsides is that they use high water consumption. Air-cooled chillers, on the other hand, use current from ambient air from fans as a means of heat transfer. So they have no cooling towers, no water wastage, and lower maintenance costs. They're generally used in more specialized cases where environmental restrictions may exist. So it really depends on each and every situation which one you would want to use.
To compare the two chiller systems, we sent a model of both of them through our model of the building. The results are posted here. Though they use the same amount of natural gas, the water-cooled chiller is the obvious winner because it uses much less electric energy, leading to about $4,000 saved per year. Over a 30-year lifespan, which is the recommended one that we were given by our experts, that saves 31 million kilobTUs, 9.1 million pounds of CO2, and $130,000. Next, we're going to go through the specialized cooling systems that we had to evaluate for our data center. Data centers' cooling systems are very important because they carry very sensitive equipment that generate a lot of heat. These cooling systems address these needs directly and keep the equipment cool enough that it can function properly. The first method that we looked into was a CRAC unit. This stands for Computer Room Air Conditioning Unit. It is essentially an air handling unit meant to only service one room, a data center, because it generates so much heat. It's a good method because it's easy to implement and very widely used, but it tends to be less efficient than other methods and cannot modulate with the equipment inside of the data center.
In-rack cooling, meanwhile, are basically a bunch of CRAC units dedicated to a certain rack directly mounted within the IT equipment. The airflow paths are much shorter, therefore it reduces fan power required and increasing efficiency. All of rated capacity can be utilized and the highest power density can be achieved, and it's targeted to the actual needs of the specific racks, serving different power densities and purposes.
So in-row cooling is pretty straightforward. It's placed in between the servers, and basically how it works is it creates hot and cold aisles. So basically, it draws warm exhaust air directly from the hot aisle, cools it, and directs it towards the cold aisle. This prevents the mixing of hot and cold air, increasing the overall efficiency.
To compare the different cooling methods, we ran simulations for each one and then compared the energy use and CO2 emissions and cost from each. The results are displayed here. As you can see, the CRAC and in-rack units are better than the in-row units and actually save the building owner a lot of money. Though the CRAC unit is a little bit more efficient and emits a little bit fewer CO2 emissions, we would actually suggest the in-rack unit. This is because our research showed that the equipment inside of a data center will be modulating a lot and changing a lot. The CRAC unit cannot modulate, and if you change the configuration of the room, the CRAC unit may become less efficient. In-rack units do not have this limitation and would therefore be able to cool the room effectively and modulate with the equipment. This is a really good example of how a simple comparison isn't always the best option in sustainability. Sometimes you have to do your research and go into very deep detail to really understand the root of the problem and what the best answer is.
So there are plenty of other considerations that we had to take into account when doing our energy modeling through OpenStudios. Basically, we had to take into account things such as the thermostat schedule, the lighting schedule, and whether the data center cooling method should be air-cooled versus water-cooled. Though we can't go over all of them right now during our presentation, our BCA will cover basically the rest of all of our modifications that we've made for our energy model.
To conclude the presentation, the following are the recommendations that we propose based on the results of our analysis. First of all, we recommend water-cooled instead of air-cooled chiller. As we saw from the results in this presentation, we saw that the water-cooled is a lot more efficient. It required less energy, it produced less carbon emissions, and also it cost less in general. Although the overall energy use, CO2 emissions, and cost for a crack unit is less than the in-row and in-rack cooling systems, in the end, we still recommend in-rack due to the following reasons. In-rack cooling is in general highly efficient. It allows targeted cooling, meaning it sends cold air to the equipment directly instead of the entire room. As racks get moved around the data center or the equipment is used more or less at a certain time period, the in-rack cooling system will modulate along with these changes. Also, custom installation is not required, meaning specific room geometries and constraints do not play a big factor. And finally, performance of an in-rack system can be easily predicted.
Here are the results of our final comparison between the original model and our model. Though our model uses more natural gas, it uses far fewer electrical energy and therefore uses less energy overall, emits less CO2, and saves over $1 million. To wrap up our presentation, we wanted to share some of the crucial lessons that we learned throughout the process. The first is that modeling is a crucial tool for sustainability. This is because sustainability is a very complex and involved issue, meaning that it's very hard to get all the factors put together and to understand how they all fit. Using modeling, we can put all these variables in the same system and see how each affects the other. It's also a lot faster and a lot cheaper than doing it by hand, so sustainability practices are more accessible and a lot easier to do.
In this project, it was important because we were able to apply the concepts that we have learned in class and use that in real world applications. It taught us a lot about the HVAC industry, and in general, it taught us what it takes to be a mechanical engineer.
To wrap up this project, we'd like to acknowledge everyone who's helped us out throughout this entire experience. First, Professor Asento Arul for helping us out and giving us this project in general. We'd like to thank our project mentors, Lewis and Griffin, for all the help and support that they've given us throughout this entire thing. And finally, we'd like to thank our sister team, the Clean Room team, Henry, Julia, and Hannah. Thank you all.